like to welcome today's speaker, the first speaker in this semester, Bryan Gaensler. Let me say a few words about Bryan. He is Australian. He studied in Sydney, did his undergraduate there, and got his PhD. Then he moved across the Pacific and across the continental US to the East Coast. He did a postdoc in MIT and the Smithsonian Institute. Then he has been hired as a professor in Harvard. He then moved back to Sydney, where he worked for 10 years as a professor at Sydney University. And now he's back in North America as a professor at the Dunlap Institute for Astronomy and Astrophysics at the University of Toronto. And he has been working on the magnetic universe throughout his career, and we will see some of the recent highlights of his research activities. So, magnets in the sky. Let's welcome Bryan.
Well, hello. Thank you so much for inviting me to Heidelberg, where it's my first time visiting, and also for coming along this afternoon. So I'm going to be talking about magnets, and if there's one message from my talk, it's that I love magnets, and I really want you to love magnets too, which I know is a big ask for most astronomers. So because if I was talking to a public audience, they would understand what magnets are and they'd feel very comfortable talking about magnets. But because you're astronomers, I know most of you are very uncomfortable talking about magnetic fields. So rather than throw you straight into astrophysical magnetism, let's start very simply with the effects that magnetism have here on the Earth. So of course, the Earth has a magnetic field, and that field has a strength of about 1 Gauss, 10 to the minus 4 Teslas for the physicists, but we're astronomers, so we'll use Gauss, 1 Gauss. And so just bear that number in mind, 1 Gauss, because we'll be talking about a lot of numbers in astronomy that are much bigger and a lot smaller than that. So what effect does a magnetic field of 1 Gauss have? Well, it's very important. It shields us from harmful cosmic rays. It produces the aurorae. Before we had GPS, of course, we navigated using compasses, and the magnetic field of the Earth points compasses north. But there's a whole branch of science called magnetoreception, or magnetoception, which studies the effect that the Earth's magnetic field has on biological organisms. And every now and then you're sitting in a talk from somebody from some different research area, and you hear a talk on that topic and you think, I want to forget astronomy, I want to quit everything I'm doing, and I just want to completely change fields. And when I heard for the first time magnetoception, I thought, this is fantastic, I want to do this instead. So let me tell you briefly about some of the things we know about how magnetic fields affect life on Earth, and then we'll talk about how magnetic fields affect everything else in the universe. So it's been known for a long time that one of the ways in which birds do their spectacular feats of navigation, they fly tens of thousands of kilometers every winter migrating from one place to another, is that they actually use magnetic field of the Earth to navigate. So of course the question is, well, how do they know? How do they sense the magnetic field? And we actually have an answer to that now. It is now known that birds have a molecule in their eyes, in their retinas, called cryptochrome, and cryptochrome actually has a quantum mechanical response to the alignment of the magnetic field. So birds, as far as we understand, don't just sense magnetic fields, they can actually see magnetic fields. Specifically, the brightness of a bird's vision changes depending on whether it's flying along a magnetic field or across it. So if a bird is flying the wrong way, their vision actually dims, and then everything lights up when they're actually flying along the magnetic fields. So because of this cryptochrome molecule, birds can actually, in some sense, see magnetic fields. So we've known for a long time, or suspected, that birds navigate with magnetic fields, but it turns out that lots of mammals use magnetic fields as well. So there's this fantastic paper by Bagol et al. It was published in Proceedings of the National Academy of Sciences, which is a very prestigious journal, and I would argue this is one of the greatest papers ever written. What they did is they used Google Earth, or Google Maps, and they used Google Maps to look for cows. And every time they found a cow on Google Maps, they measured what the orientation of the cow was. The experimental methods section of this paper is beautiful. They explain how you can tell what a cow looks like. They explain how a cow is an unsigned vector because you can't tell where the head of the cow is versus the tail. You can only tell the orientation, just like polarization. They talk about how they take into account the fact that in sometimes you could see that there was like a dog chasing the cows, so the orientation of the cows was due to being chased by a dog, or when a cow was feeding, so then the orientation depends on where the feeding trough is. They take into account the time of day because cows might like to sun their turn so that they're facing the sun and so on. And they corrected for all this, and here is data from all over the world showing you the orientation of cows. And what they find, to about 5 sigma significance, is that all over the world, many, many different countries, cows appear to statistically line up north-south.
What is the advantage for the cow to do so?
Well, I'll come to that in a moment. So there are lots of different reasons why a cow might line itself up north-south.
For a bird, I mean, it's much more obvious.
Yeah, right. It turns out that countries like Canada, where I live, are very important because high-latitude cows are the key to this experiment. Because as we know, the geographic North Pole and the magnetic North Pole don't quite line up. If you see a cow at the equator, and it's pointing north, you can't tell whether the cow is pointing geographic north or magnetic north. But if you look at high latitude cows, this symbol here marks the orientation of magnetic north, and this is geographic north. You can see that the data do suggest that cows are actually lining up with magnetic north and not with geographic north. So cows are these bovine compasses that line up north-south. As to the advantage of the cow, we don't really know, other than we presume that when cows are left to their own devices, they just feel more comfortable standing north-south. So there's not a full understanding of this yet, but the presumption is that this is some vestigial left over from some earlier phase in evolution when the progenitors of cows did use magnetic fields for something, and they still just have this residual sense of their magnetic fields. So like everything in astronomy, just like astronomy, whenever an astronomer claims some remarkable alignment that no one had noticed before, this is controversial. So a rival group, Hurt et al., and this is just like astronomy, they put a rebuttal paper saying, well, we've analyzed the same data, we bin the data differently, we use Bayesian statistics while you're a frequentist. It's all the same arguments astronomers use when they argue, and they said, we see no trace of this cow alignment whatsoever. But then the original group wrote a new paper, just like astronomy. They said, well, there's a new version of Google Earth out now with better data, and we've reanalyzed the new data, and the signal isn't just there, it's even stronger than it was before. So it's exactly the same arguments that astronomers have. The debate goes on, but all I can say is that in my heart, I know this must be true. So next time you're driving along the Autobahn, don't just focus on the road, but have a look at what the cows are doing and see if you can do a bit of citizen science yourself. And this has created a whole industry of well, yeah, it might be a bit dangerous, but this has created a whole cottage industry of other people looking for different animals and their alignments. So there's another group that walked through the famous Christmas markets in Prague looking at all the carp, the fish, swimming in buckets. And they measured the orientation of the fish in the buckets, and the fish seemed to line up north-south. And my favorite one, and this is a picture that I'm not allowed to show you, but there's a paper where they actually measure the orientation of the poops left behind by dogs. And there's an actual photo in the paper of the dog squatting down and like a protractor showing the orientation of how they measured it. And it turns out that dogs preferentially poop north-south as well. So there is this weird vestigial magnetic sensitivity in mammals. This extends to humans as well. It was shown in the 1980s that the quality of your sleep depends on your orientation to the Earth's magnetic field. So they had people sleep north-south and people sleep east-west, and they measured their brain waves, and they found the fact that people got a different quality of night's sleep when they sleep north-south and east-west. So at least, I don't know in German, but in English there's an expression of getting out on the wrong side of the bed. Well, maybe it's not the side of the bed you get out of, but your orientation of the bed with respect to the Earth's magnetic field. And this very exciting result came out of Caltech just sort of a month ago. This is this result from Wang et al. What they did is they had people sitting there and they were measuring the alpha waves from their brain as a magnetic field rotated around them. So it simulated you turning in the Earth's magnetic field. And so this is a measurement of the alpha waves, how can I get rid of that? A measurement of the alpha waves in the brain when there's nothing happening. This is a magnetic field spinning clockwise, and on the left is a magnetic field spinning anti-clockwise, and you can see that when the stimulus is turned on, the alpha waves are depressed quite clearly in most of the subjects that they studied when the magnetic field was rotating in a particular way. So again, this sort of lacks a clear interpretation, but our brains can actually sense the Earth's magnetic field, just like cows and dogs and everything else. So there's clearly a lot going on there that we don't understand. But as I said, in another life, this is what I am working on. It seems really fascinating. So what about terrestrial magnetic field, artificial magnetic field? So as I said, all of this is from the Earth's magnetic field with a strength of 1 Gauss. So being physicists, we like to make things as big and as strong, as extreme as possible. So if the Earth's magnetic field is 1 Gauss, you might ask the question, well, how strong can you make magnetic fields on Earth? So the strongest steady magnetic field that's ever been created on the Earth is a magnet in Florida, and it has a magnetic field of 450,000 Gauss. And to maintain 450,000 Gauss, you need thousands of liters of liquid helium and 33 megawatts of power. If you're not interested in sustaining a magnetic field, but you just want to know just for a moment how strong can a magnetic field get, then the record for a repeatable experiment is this magnet in Los Alamos, and a couple of years ago it reached a field of just over 1 megagauss, just for a few milliseconds. There's a great video on YouTube of all the scientists running the experiment, and the dial is creeping up, 0.9 megagauss, 0.95, 0.97, and when it hits 1 megagauss, they're all punching the air and cheering, because it was the first time anyone had ever reached 1 megagauss in a repeatable experiment. I say repeatable because there are other experiments that have gone even higher. And so the actual record for the strongest magnetic field that's ever been created in a macroscopic experiment is this experiment that was done in Russia called MC1, and they were able to create a magnetic field of 28 megagauss. So here's a graph from their data. So this is magnetic field in megagauss versus time in microseconds, and you can see the magnetic field shoots up all the way up to 28 megagauss and then stops. And you might ask, well, what happens then? Like, did it go back down? Did it stay up there? Did it go higher? And as they explain in the paper, the reason why the graph stops there is because this was done by smashing magnets together with a couple of 100 kilograms of explosives. As the paper says, these experiments definitely have to be performed outdoors. So these are the sorts of levels of magnetic fields that we can make here on Earth. Up to 28 megagauss as a one-off and 1 megagauss as a repetition. So if we now switch over to astronomical magnetic fields, I'm going to show you a whole range of different types of magnetic fields in a moment. And the two things I want you to take away from is that everything in the universe is magnetic, and that the range of the strengths of magnetic fields are absolutely enormous. So here is sort of everything I can think of that has a magnetic field, sort of staggered in orders of magnitude. And so the weakest magnetic fields that you'll actually see talked about in the literature, remember the Earth's magnetic field is 1 Gauss, but you will routinely in the literature see people talk about these very high redshift seed fields, which might be as small as 10 to the minus 30 Gauss. So that's obviously a very small number. I'm going to talk today about the intergalactic medium, where it's only now that we might be detecting magnetic fields in intergalactic medium, but they're thought to be anywhere between 10 to the minus 15 and sort of 10 to the minus 8 Gauss. Intracluster medium, we're getting towards a microgauss. Interstellar medium, a few microgauss. In the galactic center, up to a milligauss. So these are the sorts of magnetic fields I'm going to talk about mostly today. If you go to actual objects, then you get much bigger magnetic fields. Remember, the magnetic field of the Earth is 1 Gauss. The star, the main sequence star with the highest magnetic field ever measured is Babcock's star, and that has a magnetic field of 34,000 Gauss. If you go to degenerate objects, you can get much higher. So now we get to magnetic fields that are much higher than this 28 megagauss that these Russians made by smashing magnets together with dynamite. The most magnetized white dwarf known has a magnetic field of about 1 billion Gauss. The most magnetic pulsar known has a magnetic field of about 10 to the 14 Gauss. And even that is swamped by magnetars, these neutron stars with extreme magnetic fields. This magnetar, SGR 1806, has a surface magnetic field of more than 10 to the 15 Gauss, and we've indirectly measured its interior magnetic field, and that's 10 to the 16 Gauss. If cosmic strings exist, then they could have magnetic fields of up to 10 to the 30 Gauss, and if Planck mass monopoles exist, then they have magnetic fields of up to 10 to the 55 Gauss. So this is really quite extraordinary. In astronomy, we we can comprehend and seriously talk about 85 orders of magnitude in magnetic field. Now, it's worth noting that the last two are theorized but never been observed, and the top one is almost has to exist but also has never been observed and indeed may never be observed. But even if you stick to things that have actually been detected and you say, I'm only going to talk about things where we have definitely got a robust detection, there are still about 23 orders of magnitude between the weakest magnetic fields we've ever detected in the universe and the strongest, which means that magnetic fields are a wonderful playground for a whole range of different physical processes. So as I said, today I'm going to talk about these very weak magnetic fields. So how do you go about measuring a field that's as weak as a microgauss? So there's a few ways to do it, but the tool that I use most extensively is this idea of Faraday rotation. So most of you are familiar with this, but for people who aren't, or for the students, just a brief reminder, Faraday rotation is a plasma effect, it's birefringence in a plasma, that causes the planar polarization of the light to actually twist and rotate as it propagates through a magnetized gas. So the amount of rotation you get, if you start off with some polarization angle theta naught, then the angle you measure is different from the input angle by an amount Rm lambda squared, where Rm is your observing wavelength, lambda is your observing wavelength, and Rm is this integral along the line of sight of NB dl. So a couple of points that make Faraday rotation especially powerful is that it provides the direction of the magnetic field. If the magnetic field is pointing towards you, then the light twists one way, and if the magnetic field is pointing away from you, it twists the other way. So you can only measure the line of sight component of the magnetic field, but you can tell the difference between two different possible orientations of the field. And the other thing is, because it goes as lambda squared, this means that this is a completely negligible effect, for example, at optical wavelengths. But at radio wavelengths, it's a very big effect. And the beautiful thing is that the universe is almost completely transparent to radio waves. So as long as you can find a background source of polarized light, it really doesn't matter what that source is, you don't care, you can study the objects in front of it through their Faraday rotation. So indeed, even the cosmic microwave background, the most distant object we can see, is polarized. So in principle, it's a difficult experiment and it hasn't been measured successfully yet, but in principle, you can measure the Faraday rotation of the cosmic microwave background, and then you've got this giant integral that covers the entire universe from last scattering to the present. And so it's a probe of magnetic fields throughout the universe. So here is Faraday rotation in action. In this case, the background polarized source is a pulsar, although, as I said, it doesn't really matter what it is. And the way you measure it is you measure the polarization angle at many different wavelengths. So if you do this, in this case to about a dozen wavelengths, you plot theta versus lambda squared, you plot one against the other, and you get this beautiful straight line that just wraps around every 180 degrees. So this is not some subtle statistical effect. This is something you can just see and you can plot with pen and paper. And if you want to work out what the rotation measure is, then you simply just fit a slope to this line and you measure it off the graph. In this case, the rotation measure is plus 495 radians per square meter. So interpret that number of 495 as potentially complicated because you need to know something about n and L in order to extract B, but the key thing here is that the slope is obviously positive. And that means that in this particular case, you can say that the invisible gas clouds that are floating between the pulsar and us, the average magnetic field in this invisible gas is pointing towards us. So we've made a measurement of the direction of magnetic field in a particular patch of the sky. And you can imagine another situation where the slope here was obviously negative, and in that case the magnetic field would be pointing away from us. So the standard experiment that people have been doing since this effect was first seen in astronomy in the 1960s is something like this. You find some background object, you really don't care what it is, but there are radio galaxies all over the sky and they're polarized, and the light is rotated and you use that to study the magnetic properties of the object in front of it. The problem with this approach is you've only got one sight line, and the effect is an integral effect. So you don't know where along the line of sight the Faraday rotation occurs. So you've got a number, like plus 495, but you don't know whether it happened here or here or here. The solution to this is to do this over and over again to a very large number of sources. If you can do this to a very large number of sources, including ones that actually go past the object, then you can actually start to work out what the foreground is, what the background is, and what the magnetic field of various objects are. It turns out this is very challenging because polarized sources are faint. There's very few of them in the sky, relatively speaking, and if you want to map wide field parts of the sky, you run to all these complicated instrumental effects involving wide field polarization calibration. But over the last 10 years, we've overcome those challenges, and so we can now make wide field views of lots and lots of polarized sources, and so we can take this approach that I call the rotation measure grid. So what I'm going to do is I'm going to talk to you about some of the applications of the rotation measure grid and how we can use that to map out magnetic fields throughout the universe. The simplest thing you can do is just pick an object, some discrete object on the sky, a nebula or a galaxy of some sort, and you find background polarized sources behind it to map out its magnetic field. And the state of the art in doing this, and this is an important number, I'll come back to it in a couple of slides, the state of the art is about 1 to 3 rotation measures per square degree. So even with the most powerful radio telescopes we have now, telescopes like the VLA, you can only find about 3 polarized sources in a square degree, which is not very much compared to the number of radio sources that you get in total, or indeed the number of optical galaxies you would hope to get in a square degree. So you can only really use this technique if you've got an object which is many square degrees across. If you want to study a galaxy that's 1 arc minute across, you have no chance of finding a polarized source behind it. But here's an example of the sorts of things you can do. This is a big object that's more than 25 degrees across. This is a large neutral cloud called the Smith cloud. And it's a high velocity cloud. It's one of these clouds that are not rotating with the galaxy, but seem to be falling into the galaxy at quite high speed. Now there's a few mysteries about high velocity clouds, and one of them is how they even exist at all. Because we know how fast the cloud is falling into the halo. We know the associated ram pressure and stripping associated with that speed of falling, and we know the time scale it takes for them to fall into the disk. And if you put all those numbers together, these clouds should not exist. They should have been shredded to nothing long before they got to where they get in the halo. So it had been proposed in a hand-wavy way that maybe magnetic fields somehow protect these clouds from being destroyed, in the same way that we invoke magnetic fields whenever there's anything in astronomy that we don't understand. So we actually put that to the test, and this is work done by a student, Sarah Betty, and a postdoc, Alec Hill, and a bunch of others of us. We measured, so each one of these symbols is the position of a background radio galaxy. So these have got nothing to do with the topic of my talk. These are distant supermassive black holes, AGNs, shooting out jets and lobes, but we're using them as polarized background sources. So for every one of those, we measure the Faraday rotation. Those symbols mark the positions of AGN. Red symbols are AGN that have a positive rotation measure. Blue are ones that have a negative rotation measure, and the size of the circle corresponds to the magnitude of the rotation. So what you can see is that there is enhanced rotation measure through the cloud, and there is extra enhanced rotation measure around the rim of the cloud. So what we seem to see here is a magnetic field that's actually being draped, that's being swept up and draped around the cloud as it plunges down into the Milky Way. You can work out that the line of sight component of this is about 5 microgauss, and that indeed is strong enough to sort of act as a shield and prevent the high velocity cloud from being stripped. So indeed it seems that magnetic fields are the answer here, and we've now done this in about 3 cases, so this is the most spectacular one. The high velocity clouds are magnetized, and the magnetic field is wrapping around the cloud and protecting it from being stripped apart as it falls into the disk. Something on even larger scales is here. You're probably familiar with our friends, the Large Magellanic Cloud and the Small Magellanic Cloud, but not all of you might know is that there is a bridge of gas connecting the two, the Magellanic Bridge. And this is a tidal feature that is due to the 2 galaxies interacting with each other and with the Milky Way. So we had used this technique, the rotation measure grid, to show that the Large Magellanic Cloud is magnetic and the Small Magellanic Cloud is magnetic. But the new thing that we've done the last couple of years is show that the bridge is also a magnetized object. So this is work by my recently graduated PhD student, Jane Kaczmarek, and we used 167 background galaxies in this region. And what you can see is the symbols here are all quite small in diameter. A plus means that they're essentially consistent with zero. So you can see essentially zero rotation measure out here, zero, more or less zero rotation measure down here, but a whole lot of blue circles along the bridge. So we're seeing enhanced magnetic fields along the bridge joining the two galaxies. And we can actually isolate two components here. It's got an ordered component of the magnetic field of about 0.3 microgauss, and it also has a turbulent component which is about 3 times stronger than that, which is 1 microgauss. And so this is consistent with not just the gas being ripped off the galaxies, but the magnetic field actually being ripped off the galaxies as well. So there's actually a magnetic flux tube joining the two galaxies. Back in the 1970s, people used to speculate the idea that there's just a single pan-Magellanic magnetic field, that you should not consider the magnetic field of these galaxies as separate, but as one giant system with a single geometry, and this experiment seems to confirm that there is really one giant magnetized structure that is being shaped by these galaxies and by the tidal interactions between them. So this is what you can say. This is in our own Milky Way, and this is in the neighborhood of our Milky Way. Let's now talk about other galaxies. One of the things we'd really like to do is to measure the magnetic field in our own galaxy, which we've done, and then do the same thing at galaxies at higher and higher redshift, and to see how the magnetic field of galaxies actually evolve with time. Because if we could plot magnetic field versus time, or magnetic field versus redshift, we'd understand how magnetic fields are generated in galaxies. So sort of the holy grail is to measure a magnetic field of a distant galaxy and show that its magnetic field is systematically weaker or more disordered than our galaxy, so you could actually conclude that the magnetic field in that galaxy hasn't yet been built up. So this is hard because a galaxy that's at an interesting redshift is so small that you have no chance of finding a background source behind it. So we came up with a clever way of getting around this problem. So this is work that I've done with Anne Mao, who's going to talk to you at the end of the term, and that's to use gravitational lensing. So what we do is we find a polarized background source with a galaxy in front of it, and the polarized background source has actually been lensed. So one of the ray bundles goes right through the intervening galaxy, and one goes around it. Both components are polarized. They're the same background source, and they both experience Faraday rotation, but the amount of Faraday rotation they experience is different because of their very slightly different path lengths through them. Their path length through most of the intergalactic medium is the same, their path length through the Milky Way is the same, but at the site of the lens, one travels through the galaxy and one doesn't. And so the difference between those directly gives you the in situ magnetic field of a distant galaxy. In this case, the galaxy is a normal spiral galaxy at a redshift of about 0.4, and here's a graph showing you the polarization of the ray bundle that essentially misses the galaxy, and you can see the rotation measure is consistent with 0. And in blue, the ray bundle that goes through the disk, and you can see the rotation measure is different, and it's about 500. So if you take the difference between those, you have now measured the magnetic field in situ of a galaxy that's billions of years younger than our own galaxy. And I won't go into the details, but you can show that the magnetic field on the disk has two components. It has a coherent component, which is about 10 microgauss, and a random component, which is about 15 microgauss. And this is a bit of a surprise, because those are essentially the same numbers that you would expect to find in the Milky Way. If anything, they're actually even a little bit stronger than the magnetic field in the Milky Way. So that tells you that by the time you get from when galaxies are formed to a redshift of 0.4, that the magnetic fields that we see today have already been essentially established. That gives you an upper limit on the timescale it takes to set up magnetic fields in the universe. If you think that that magnetic fields in galaxies are generated by dynamo action, which is what we do think, then this tells you that the e-folding timescale of the dynamo has to be faster than about 240 million years. This is a really frustrating number because, of course, that's around the timescale of a rotation of a galaxy. So this cannot rule out the fact that just normal, boring galactic rotation is all you need to generate magnetic fields in the universe that we see today. The next step, which Anne and I am going to bond tomorrow, and Anne and I are going to sort of progress this further with data we have, is to look at more lenses, hopefully at even higher redshifts, and start to either see an epoch where magnetic fields are actually being amplified, or to push this number down even further to start to actually distinguish between simple dynamos that invoke rotation of the whole galaxy versus more complex dynamos that require other, faster effects. So this is just on one galaxy. So this is galactic magnetic fields. What about intergalactic magnetic fields? When you find a distant object and you measure its Faraday rotation, you are getting Faraday rotation all along the line of sight, including the magnetic field in the intergalactic medium. And we'd really like to measure the magnetic field in the intergalactic medium because that's in principle a direct probe of how magnetic fields were created in the universe. There are different models for how magnetic fields are generated, and they make very different predictions for what the magnetic field of the intergalactic medium should look like. So here's some really interesting work that just came out. I did not do this. This is from Shane O'Sullivan in Hamburg. And what he did is he used LOFAR to study a double radio galaxy. So here's a radio galaxy. So the galaxy is in the middle, and here's a lobe up here, and here's another lobe down here. And he measured the Faraday rotation of the top lobe and the bottom lobe. And because he used LOFAR, which operates at very large values of lambda squared, you can get very small errors in your measurements. And so he was able to show exquisitely that the difference between the rotation measure of this lobe and the rotation measure of that lobe is just 2.5 radians per square meter, a tiny, tiny number. And if you look at these studies of large-scale structure, you can see all of these different filaments of large-scale structure lying in front of the galaxy. And so you can see that this northern lobe has a whole bunch of different filaments lying across it, and this lobe only has one. So one possibility is that the reason why these two Faraday rotations are different is because of the magnetic fields in the intergalactic medium in these filaments. And if that's true, then you can work out that the magnetic field in these filaments are about 300 nanogauss. However, these two lobes are about 8 or so arc minutes apart, and the Milky Way is a very complicated place. Every spot you look at in the Milky Way has a different Faraday rotation, so this has got Milky Way components in it as well, and you can see there's a lot of mottleness, a lot of variation. And so we can't rule out that the difference in this 2.5 radians per square meter is not due to the intergalactic medium, but is simply due to turbulence in the medium of our own Milky Way. So we saw this result and thought, this is really neat, but you can never know whether this is just galactic foregrounds, which is a very boring answer, versus intergalactic medium, which is a very exciting answer. But we figured out a way we think we can get around this. So this is work done by my recently departed postdoc, Tessa Wernström. What we did is we looked at every polarized radio source in the entire sky, and we found every case where there were two polarized sources near each other, so a double source, anywhere between 1 arc minute and 20 arc minutes apart. If you do that, you find about 5,000 pairs, and then what we did by hand is we went through and determined whether each of those two polarized sources was a physical double, or just two random sources at different redshifts that happen to sit near each other. So here's an example of a nice physical double. So these are two polarized sources. They're clearly part of the same source, and they're separated by about 6 arc minutes. And here is an example of a random double. Here is a source here, and a source here, and these sources are unrelated sources at different redshifts about 9 arc minutes apart. And we know they're unrelated because this one here is actually part of a double right here. So if this is a double, then presumably these two sources are different. So this was a lot of work, but when you do this, you get about 300 physical pairs, so two polarized sources, both with Faraday rotation, where they're coming from the same distance, and at 5,000 where they're projected nearby in the sky, but they're at different distances. So now we can repeat the experiment that I showed you on the previous page, but we can do it for two different sets of sources. One's where the sources are basically going through almost identical sight lines, and one where the part of the Milky Way is the same, but the part of the intergalactic medium is different. And, whoops. What we found is that for the physical pairs, the RMS difference between this lobe and this lobe is about 4 radians per square meter. So that's not too different from the 2.5 that the LOFAR group measured. But when you do it for random pairs at the same separations, you get 15 radians per square meter. And so here's a graph of our data. This is the variance. Here is the variance for random sources, and here's the variance over the same range of separations for physical sources, and you can see they're completely different. And so you don't have to worry about foregrounds now, because all the sources are being seen through the same foreground. Any difference between these must be due to the fact that one group of sources are physical pairs where they're right next to each other, and the other ones are random. So, the simplest and hopefully the most exciting possibility for this is that this is actually due to the intergalactic medium. So here's a diagram of a random pair. You've got one source here and you're looking through some foreground stuff, and you've got another source here and you're also looking through the intergalactic medium behind the first source. If you invoke this interpretation, then we have directly measured the magnetic field of the intergalactic medium, and it's about 40 nanogauss, which is in line with some cosmological predictions. So this is using old archival, reasonably crummy data from the NVSS. The data is 20 years old. We're now in the process of getting new data with the VLA, both to confirm this effect and to get a bigger sample. But the key thing here is the technique of comparing random pairs and physical pairs is a way to break this degeneracy and to measure the magnetic field that's behind one part of the pair and in front of the other. So where do we go from here? Well, we need more sources, and we're doing two projects to get more sources. One is with this telescope in Australia, the Australia Square Kilometre Array Pathfinder, or ASCAP. And the really exciting thing, it's like a mini VLA. It doesn't have anywhere near the sensitivity of the VLA, but it has something that's completely game-changing, and that's that it has a 30 square degree field of view in a single pointing. The VLA's field of view in a single pointing is 0.2 square degrees. So you'd have to do 150 pointings with the VLA to get one pointing with ASCAP. And one of the flagship surveys with ASCAP is a survey that I'm leading, the Polarization Sky Survey of the Universe's Magnetism, or POSSUM, and we'll cover the entire sky to 20 microjancies of sensitivity in full polarization. Now, if you remember, I said the state of the art is about 1 to 3 polarized background sources per square degree. With POSSUM, which will start later this year, we're going to have the entire sky with 50 sources per square degree. So that's going to be completely game-changing in terms of the quantity and the quality and the quantity of what we can study. In the north, we're also involved in something called the Very Large Array Sky Survey. It's at a different frequency, different resolution, different sensitivity, so it's a somewhat different survey, but it will give us rotation measures for 200,000 sources in the northern sky, and we have an initiative in Canada, Sarada, to process all this data. What's exciting is there's actually 10,000 square degrees where the two surveys overlap, so there'll be about 60,000 sources for which we have 1 gigahertz data from ASCAP and 2 to 4 gigahertz data from the VLA, and we can put that all together and do very broadband studies with redshifts and optical spectra and do all sorts of fancy things involving what's happening in the source and what's happening in the foreground. And so we haven't started the survey at POSSUM yet. VLAS and POSSUM, VLAS has just started and we haven't got the polarization working yet, and this survey will will start at the end of this year. But I just want to show you a preview of what you can expect. So if you remember, I said the best we can do right now is about 3 rotation measures per square degree. So this is work done by my student, Shannon Vandervood, and so this is just for 28 of the 36 antennas and only 4 hours of observations. And this is an observation that happened to be centered on the supernova remnant 1006. So if you look carefully, you can see all these little dots in the background. So this is in our Milky Way, and all these little dots, background AGN, and Shannon was able to measure Faraday rotation for 516 of these sources. So this, even with only 4 hours of data and only 28 of the antennas, we're now getting 17 rotation measures per square degree. So pick your favorite object, draw a circle marking the size of your favorite object on here, and you get all of these rotation measures through it. And as I said, we hope to push this number up once we get the full array going up to 50 rotation measures per square degree. So this is just a few weeks old. You can see there's still some issues with the data. There's some artifacts and so on. But this is very encouraging for the way forward, and that we're really going to move into a spectacular new regime. I want to finish by talking about something a bit different, which is one of the most exciting things happening in astronomy right now, which are fast radio bursts, or FRBs. These are a complete mystery. We do not know what these things are. We know that they're fast, they're radio, and they burst, and that's about all we know. So they're very bright, they're very frequent. We think there's probably at least one, anywhere between 1 every 10 seconds and 1 every minute somewhere on the sky. So there's been 30 or 40 fast radio bursts just during this colloquium. They only last for a few milliseconds, and we know that they are extragalactic objects. They're at cosmological distances. We've seen them out to redshifts. We've definitely seen them out to redshifts about 0.4, and there are some that don't have redshifts yet that we argue are as far away as a redshift of 3. So of course there's an exciting question is what are they? We don't know. But they're also fantastic probes. As far as we know, they're polarized. So we can measure their rotation measures, just like we can for AGN, and so that can tell us something about the fast radio bursts themselves and also about the intergalactic medium. And because they're pulsed, you can actually measure another propagation effect, the dispersion measure. If you recall, the rotation measure is the integral of n b dl. Well, the dm is just the integral of n dl, so it counts how many electrons are along the line of sight, so you can directly get the magnetic field. If you just divide Rm by dm, the b's cancel, and you have the magnetic field along the line of sight. So what can you do with these probes? Well, let's just talk about what you can do with one fast radio burst. There's one fast radio burst that's different from all the others, and that's because it repeats. Most fast radio bursts we've seen only happen once, and you never see it again. But there's this one, 121102, which has repeated. It's not periodic, it's sort of random, but we've seen it at the same position hundreds of times. The first time they saw it, it had a, sorry, that should be DM, not DDM. It has a DM of 559.7. But its rotation measure was enormous. It was 103,000 radians per square meter. Remember, the numbers we've been talking about before now are like 20 radians per square meter or 100. There's a few sources in our Milky Way that have rotation measures of 1,000. This object had a rotation measure of 103,000. Even stranger, when the group that discovered this object reobserved it 7 months later, its dispersion measure had changed slightly. It had gone up to 565, so it changed by 1%, but the rotation measure had dropped down to 94,000. And I believe they've been observing it since then, and it's still going down. It's down to about 40,000 now. So you've got to ask the question, what is going on? How can you have an object whose dispersion measure, the number of electrons in front of it, barely changes, but the rotation measure seems to be dropping dramatically? And we don't know. There's a number of explanations for this, but the explanation that I propose with Tony Pirro is that this is the signature of a very young supernova remnant. So there's an idea from Brian Metzger, who's coming later this term to speak to you, that fast radio bursts are young magnetars, this very young, energetic, violent neutron star that occasionally is burping or flaring and sending off a fast radio burst. But if you have a young magnetar, it must be inside an expanding supernova remnant. And Tony Pirro and I said, well, what would you actually measure if you had a polarized source embedded in a young supernova remnant? And if you calculate this, it turns out that you should get a very high rotation measure, but just drops rapidly as the supernova remnant expands. At first, the dispersion measure drops, but then at around 100 years, the dispersion measure just remains flat. Because what's happening is the dispersion measure of the ejector is dropping, but the dispersion measure of the swept up material is increasing. And so there's a place at around 100 years where the two cancel out. So if you plot dispersion measure versus rotation measure, then the prediction you get for a fast radio burst under this model is that it sort of follows, as the system ages, it goes down and to the left, and then it flattens out for a while, and then it starts to go up again. So if you actually put this particular object on a plot, it sits about here, and indeed, according to our calculations, if fast radio bursts are young neutron stars sitting inside supernova remnants, there should be a period around 100 years after the explosion where the rotation measure is dropping, but the dispersion measure is not changing. So obviously there's only one object. What we really need is another repeating fast radio burst. So as I'll talk about in a moment, we've now discovered a second one, and we've now measured its rotation measure as well. I'm not allowed to tell you what the rotation measure is, but suffice to say that we now have a second object, and we can now say whether this is a unique object or whether the same property is seen in other objects as well. So that's one fast radio burst. What could you do with hundreds or thousands of them? You can actually probe the intergalactic medium. So as I said earlier, the dispersion measure is a count of the number of electrons, and the rotation measure is a count of n times b. So in simple circumstances, you can directly get the magnetic field of the foreground, in this case the intergalactic medium, just by dividing the rotation measure by the dispersion measure. So with Takia Akahori, we asked the question, does this actually work? So we set up a cosmological simulation with magnetic fields, and then we set off fast radio bursts throughout this volume and measured their rotation measure and the dispersion measure. So here was our input simulation. So in this particular case, the magnetic field of the intergalactic medium doesn't really evolve much with redshift, and it had a strength of about 20 nanogauss, not too different from what we measured in that earlier experiment. If you now measure fast radio bursts all throughout the universe, and you just divide Rm by Dm, then this is the magnetic field that you recover. So it actually gets the answer wrong, And the reason why is because the rotation measure and the dispersion measure are not coming from the same parts of the intergalactic medium. One is coming from filaments, and the other one is coming from voids. So you actually have to introduce a little correction factor. If you use a slightly more complicated equation, where you correct for the mean redshift of filaments, and you correct for the fraction of the total dispersion measure that's in filaments. And these numbers only depend on your cosmological model. They don't depend on any properties of the fast radio bursts. So if you use this formula instead, you can actually recover the magnetic field of the intergalactic medium. So if we have a sample of fast radio bursts whose rotation measures aren't 100,000, but are low numbers suggesting we're just measuring the intergalactic medium, then we now have a mechanism to actually measure the strength of the field in the intergalactic medium. And it turns out we're measuring the rotation measures of more and more fast radio bursts, and many of them do have magnetic field, rotation measures that look like it's this pure intergalactic medium. There's no contamination from the environment local to the source. So if we can do that, not only can we measure the magnetic field of the intergalactic medium, but we can actually ask, where is that magnetic field coming from? So here's work I've been doing with Stefan Hackstein in Hamburg, where we're trying to distinguish whether magnetic fields in the universe are primordial, that is, they were created by some exotic process very early on and just been there ever since, or whether magnetic fields are astrophysical, they've been injected into the universe by black holes and stars and supernovae. And so we're relying on the fact that from its early days, but as far as we can tell, there are some fast radio bursts that don't appear to have any contamination from their host. The Faraday rotation that we're measuring is just the intergalactic medium. And that's much nicer than radio galaxies, which have all these complicated effects associated with the emitting sources themselves. So if fast radio bursts are pure prods of the intergalactic medium, then you can do a simulation like this. This is at a redshift of 0.1, showing you the distribution of rotation measures that you expect for fast radio bursts if magnetic fields are primordial versus if they're astrophysical, and you can see that there's no difference. But if you do this at a redshift of 0.5, you can see that there are actually differences. You expect a different distribution of IgM Faraday rotation for an astrophysical magnetic field in the universe versus a primordial one. So what worked out is that we only need about 100 fast radio bursts, all at a redshift of half, and all with rotation measures. And if we get that, we can actually distinguish between primordial and cosmological and astrophysical magnetic fields. All right, so that's just been a quick journey through some of the things that we're doing with Faraday rotation and polarization. So just to summarize, this is a very exciting field. There's lots that's happening. Covers a whole range of topics across astronomy, from the intergalactic medium to magnetize and everything in between. And that this has now finally been made possible by the fact that we've worked out how to robustly do this sensitive wide field polarimetry, which is a very difficult undertaking. So I've talked about three things today. I've talked about this concept of the rotation measure grid, which allows you to measure strength and structure of magnetic fields in anything at all that's in front of you. I talked about a high velocity cloud and about the Magellanic Bridge, but you can do this to all sorts of things: galaxy clusters, external galaxies, the entire Milky Way. I talked about how you can use radio galaxy polarization and gravitational lensing to do things like measuring the magnetic field of galaxies as a function of redshift and to detect the magnetic field of the intergalactic medium. And I finished by talking about fast radio bursts, which might be finally the way to distinguish between the different possible explanations for where magnetism in the universe actually comes from. But the bottom line is that finally now, after years of waiting, I think we're finally, with these new projects, starting to see what the polarized sky actually looks like. And we're poised to explore the full magnetic universe in the next year or two with ASCAP and with the VLA Sky Survey and with CHIME, and in the decade ahead with the much more powerful Square Kilometre Array. Thank you very much.
So thanks, Bryan, for this great overview of the indeed magnetic sky from Earth to the primordial universe to the most powerful quasars. The podium is open for discussions. Yes, I start with Kees Dullemont.
Yeah, very nice talk. I was particularly fascinated by these high-velocity clouds and the magnetic fields protecting them from being stripped. So just from a theoretical perspective, how is it understood how these clouds get entrained in sufficient amount of magnetic field that they can be protected? Or has there been simulations that show how this works? Or?
There's a few early simulations that I think they're relatively simple, but there have been a couple of simulations published in just the last couple of years that actually have a seed field in the cloud, and they have it interacting with the halo, and it builds up, and it does seem to work. But I think there's a lot more to do here in terms of actually properly modeling the thermal conduction. The other thing is, of course, is that these clouds are defined by being neutral, but when we use Faraday rotation, we're only studying ionized gas. So we have to make some assumptions about the composition of the cloud and how the ionized gas and the neutral gas are mixed together, or is it just an ionized sheath around the outside? These are all things that need to be explored properly through simulations.
Further questions? Andreas, just let me.
So I have a simple question about these fast radio bursts. You explained us that which are the sources, it means magnetized and supernova remnants, but how are the bursts itself formed? Why do we have repeated bursts? Why you have this millisecond bursts? What happens there?
Well, we don't know, but in the model of Metzger, the bursts are produced by some sort of maser-like emission. And what happens, we know from work that I did in 2005, that occasionally, once every few decades, one of these magnetars gives off a massive reconnection event, some sort of flare. And that blasts off about 10 to the minus 9 solar masses off the surface of the neutron star into space at about half the speed of light. So you get this small amount of mass moving very quickly, which drives this shock into its surroundings. And so what Metzger et al. Has proposed is that each time this happens, that shock catches up with the shock from previous outbursts, and that collision generates all these maser instabilities that generates these random beamed flashes of coherent radio emission. So the process is stochastic. It's associated with the collision of the two shocks, but you might get many bursts spread randomly out over several years or decades during the interaction process. So that's for the repeating bursts. We don't know if all bursts repeat. Maybe some just only repeat once every 100 years and some repeat every 5 minutes. But for the ones that don't repeat, they could have a completely different explanation that might involve some sort of explosion or something like that. So we still don't even know if there's one class of fast radio bursts or multiple classes. With gamma ray bursts, of course, we now know there's about 5 or 6 different classes of gamma ray bursts that represent everything from solar system events to merging neutron stars. But CHIME will hopefully tell us very conclusively whether there's just one class of fast radio burst or multiple classes.
So next question, Stefan Jordan.
On your last slide, you showed this nice picture of probably M551 with the spiral arms and the direction of the polarization of the magnetic fields. Is it easy to understand why they are so much oriented along the spiral arms?
The short answer to that is no. This picture is a little bit misleading because it just looks so simple. There's other galaxies where the arms don't appear to have a well-organized magnetic field, and the magnetic arms are between the spiral arms. There's other ones like the Milky Way, where the Milky Way, we believe, has magnetic spiral arms, but they have a different pitch angle from the starlight spiral arms. So the short answer is no, it's not easy to understand. We think that there's different things happening in different galaxies, that some dynamo modes produce spiral arms that are strongly aligned with the spiral arms and some aren't. I don't know, I know there's a few people here who've been simulating galaxies and magnetic fields. I don't know if you can comment on whether you see the same diversity in the simulations.